Okay, so we've been talking about refraction. Now it's time to mention a very specific thing that can happen with refraction in terms of different media that light can pass through. So this phenomenon is called the critical angle, and it involves a very specific way that the incident ray inside of a denser material interacts with the boundary of that material with the air. Alright, so here we have an example of water, and we have a ray coming in. Right, actually, let's back up to this example. A light ray is coming out from the water, and of course, when it leaves the more dense medium, enters the less dense medium, the direction bends away from the normal line. So angle theta 2 is bigger than angle theta 1, right? Bigger angle is in the less dense medium. So if I make this angle larger, this angle gets even larger. If I make this angle large enough, then the refraction angle is 90 degrees. Alright, and this is called the critical angle. This is the angle of incidence inside the water that results in a 90-degree refraction, right along the boundary of the material. Okay, that's what's called the critical angle. As soon as you pass the critical angle, you get what's called total internal reflection, and you don't get any refraction at all. None of the light comes out from the more dense medium. Alright, so total internal reflection occurs when the light inside an optically dense medium strikes the boundary greater than the critical angle. We have a picture of this here. So there we have a laser light. It's striking this surface at the normal line because it is a tangent, or what do you call that? This is aimed at the center of the circle, and we know that a radius of a circle always touches the edge of a circle perpendicular to the tangent. Anyway, if I draw in a normal line here, bottom line, bam, if I draw in, that's the surface, and we'll see that the light ray is striking that at a 90-degree angle. So that's a tangent to the curved surface, and the light ray is striking perpendicular to that, so the light ray is on a normal line, which means it does not bend, which you probably notice, it does not bend. So it just goes straight into the material, though it does slow down, but since it's on the normal line, it does not bend. That's that special case that we were mentioning in the previous video. And then we strike a boundary between this dense material, which is plastic or glass, and air. Air is over here, glass or plastic is right there. So if we are greater than the critical angle, which right now this is at an angle of 50 degrees, and for most plastics or glass that is greater than the critical angle. So here we go, bam, more than the critical angle. No refraction occurs, you can tell that there's no light over here. All of it reflects. That's called total internal reflection, and that's what occurs when you strike the boundary of a dense medium with a less dense medium, and you're at greater than the critical angle. So the end result is that all of the light reflects and remains inside the medium. None of it refracts, and this has some very interesting applications. Alright, one example is called fiber optics. You can shine a laser light into one end of a fiber optic cable. I'm not sure which end is having the light shine in. It might be this one. In any case, one of these, somebody is shining a laser into one end of this, and it's coming out the other end. And you'll notice you don't really even see it on the inside of the tube. There's a reason for that. If you were able to see it, that would mean that light was escaping from the tube and entering your eyes. You can't see it, right? That means there's not any light getting out. This doesn't count. This is light that's coming out from the tip here. And this light here is reflected off of that. So looking at this part, you don't see any light. And that means that it's all being kept inside the tube. Whoa. total internal reflection. Another example. This is a little bit fuzzy, but hopefully you can see what's happening here. Somebody has taken a laser right there and shined it into this glass block at an angle greater than the critical angle, and you can see the light bounces off the bottom, then off the top, then off the bottom, then off the top, bottom, top, bottom, top, somewhere in there, bottom, top, bottom. It's bouncing around inside this thick pane of glass here. And you can literally see it happening. Bouncing all inside. It's bam, right there like that. That is totally cool. Totally cool. And then one more example. That's just some fiber optic light decorations. Somebody shines, might even be a fiber optic flashlight thingy with the little flappy plastic things at the end. One of those toys. Anyways, the light is on the other end here behind all of this, and then it shines through the tubes and comes out the ends. But almost none of the light escapes along the tube. So, fiber optics. So how does a fiber optic cable work? Well, it basically functions by taking a light input at one end of the cable, and it transmits that light all the way to the other end by taking advantage of total internal reflection. Now, what is this used for? Well, it's used for rapid data transfer, communications, applications of all sorts. If you can pulse laser light according to various computer coding, then you can basically send messages over very long distances very quickly. This is fiber optic technology if you've ever heard about it. It's very, very fast. Fast? How fast? As fast as the speed of light. Yes, nothing is faster. So, very fast communication applications. But what else could you use it for? Well, there are medical applications. If you've ever heard of laparoscopic surgery, they use a camera that takes advantage of fiber optic cables in order to look inside and see what they're doing, and then they don't have to cut you totally open. They just need some slits to put their tools in, and then they need the slit to put the camera in, so you have several smaller slits instead of one giant one. Another application would be like a colonoscopy. If they go to check for cancer inside your colon, imaging of blood vessels, they can stick a fiber optic camera into your blood vessels and look for blockages. They can look for foreign objects inside your throat or ear. They can perform surgery. Sorry, that's what I was just mentioning with laparoscopic surgery. This is an example of using a bronchoscope to look at the airways inside the lungs of this guy. So they can stick this thing down in there, and using the fiber optic technology, they're able to shine light in there, and then the light comes back up the tube, and they can see what's going on inside his bronchioles, or whatever those are called. Anyway, his airways in his lungs. So cool. There are so many applications in medicine and communication for fiber optic cables. And they really make life a whole lot better in a lot of ways for people. So, anyway, that's it for this video. I hope it's helpful. I hope that it helped you to understand critical angle and total internal reflection in fiber optics. And we'll see you next time. Thanks for watching.